Okay, so when we last left off, we were discussing electrophilic alkene addition. And so let's talk a little bit about the stereochemistry. Let's talk a little bit about the stereochemical outcome of electrophilic alkene addition. Okay, so first and foremost, after protonation, we have two possible attacks. We can attack our carbocation, which is planar from either the top or the bottom. As a result, we end up with a mixture of stereoisomers and a racemic mixture of stereoisomers in most cases. Now, that's not to say these reactions can't be manipulated to give a little bit of stereoselectivity. So you can end up with some biasing of your stereochemical outcome if there is steric hindrance on one face of the molecule. So for example, does everyone notice how we have this large T-butyl group on the top face of our molecule? So this large T-butyl group blocks the top face. And as a result, our approach is generally going to be constrained from the bottom face of our molecule. This is why we observe our bromine on the bottom face. It adds from the least hindered face. So if we had a choice between two faces, because there's an external bulky group on one face of our molecule, we end up with a little bit of stereoselectivity. This is a somewhat minor case, but we'll see similar substituent effects for other chemical reactions. Okay, let's keep going with this idea, and let's talk a little bit about how exactly do we prepare alkenes for these reactions. So alkenes are commonly made via elimination of HX from an alkyl halide. We call this dehydrohalogenation. So typically we use heat and a strong base because eliminations themselves are favored when you increase the temperature. You can also eliminate water from an alcohol using strong acid and heat. Sulfuric acid is the acid of choice for this process because it's a dehydrating acid. So mechanistically for our first reaction, the hydroxide is going to pull off a proton and we eliminate our halide. Mechanistically for our second reaction under acidic conditions, first and foremost, we are going to protonate our alcohol to make it a better leaving group. Then our alcohol is going to leave to generate our carbocation. And then finally, our solvent or another weak base will remove our proton and will eliminate to generate our alkene. We'll focus more on these mechanisms in later chapters. I'm just showing you the mechanisms now for your reference. Okay, so these are how we make these alkenes that we use for a range of derivatization reactions. So let's talk a little bit and let's try to predict the products of some addition reactions. So let's try to predict the products from the following reaction. If more than one more than one enantiomer would be correct in this case, is generated, specify each enantiomer. So looking at the following molecule, we're doing this under acidic conditions with water. So what type of reaction springs out to us if we're working under acidic conditions and we have a nucleophilic solvent? What reaction conditions does this remind us of from last class session? If we have an alkene and acid, what are we going to make? And don't be shy to type in the chat and provide some input. So if we have an alkene under acidic conditions, what are we going to generate as an intermediate? In alkene addition under acidic conditions, we're going to make a carbocation, exactly right. And we have two choices. Would we either make a secondary or tertiary carbocation? Secondary or tertiary, what's preferred? Tertiary, by far, okay? So we're going to take our acid, which we'll write as just H3O+. And this may help us visualize a little bit about what's going on here. So just like in HCl, for example, we have a proton and then we have our nucleophile. Okay, so first things first, we are going to protonate our alkene and we're going to make the more stable tertiary carbocation. Okay, so this process, of course, is reversible. Now, once we have our small amount of tertiary carbocation, what is our nucleophile? What is our nucleophile in this case? What is our nucleophile in this case? What is our electron-rich species? What is our electron-rich species? So what's going to attack the carbocation? And I see some people typing water. Yep, that's exactly right. So water is going to attack our carbocation, and that in turn will generate a mixture of tertiary alcohols. Well, not quite the alcohol yet. Okay, so water attacks, we generate this addition product. And then finally, water is going to deprotonate to generate our final tertiary alcohol. And we can choose to draw this with dash wedge notation. It's sort of redundant because this compound is meso, but we of course get a mixture of products, which in this case, these two products are exactly the same because this is a meso compound. Okay, perfect. So we protonate our alkene, we add our nucleophile, and we report our product. Does this make sense to everyone? Does this mechanism look similar to what we've seen before? The only difference is this time we're adding water instead of our halide. Any questions on this example? Would everyone feel comfortable working on one of these examples on their own? Okay. So let's give this a shot now. So I'd like you to draw a mechanism for the following reaction. So under acidic conditions in the presence of water, I'd like you to draw a mechanism for how this product is generated. So don't be shy to break out the annotate feature and try drawing the mechanism for this reaction. And I'd like to see at least one response using the annotate feature. So let's take about 2 to 3 minutes to work on this problem. In terms of the page number, it's page 39 of the chapter 7 notes. And the revised notes are posted on Canvas. Yep, so we protonate our alkene. Try drawing the product in a separate line. So after your first arrow pushing step, you draw the intermediate and then you keep going through the mechanism. And just to help this person drawing out, would everyone think, are we going to make a secondary or tertiary carbocation? Secondary or tertiary? Yep, tertiary. It's more stable by far. Okay, perfect. So we have our carbocation generated, and what's going to attack our carbocation? Yep. So instead of OH, it would be H2O. So water would be attacking. Since we're not going to have hydroxide under acidic conditions. So I see a lot of good steps so far. Allow me to clear and allow me to show a few details that I'd like you all to note in your mechanism, but the key steps were noted quite accurately. So let's talk a little bit about this. So first and foremost, we're going to draw our acid. It was correctly noted that our acid is H3O plus. You want to draw your lone pairs. We draw the attack from our nucleophilic pi bond to our electrophilic hydrogen, and the electrons in this hydrogen-oxygen bond get kicked to oxygen. We now have the following tertiary carbocation intermediate, as was very accurately noted. And now our nucleophile, which is water, you draw your arrow going from the nucleophilic lone pair to your carbocation, and that in turn generates our tertiary protonated alcohol. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, and now water removes the proton. And that's how we generate our product. Just always make sure when you're drawing arrow pushing mechanisms, your arrow goes from your nucleophilic lone pair or alkene to the electrophilic site, be it an atom. Yeah, generally the electrophilic atom. But overall, the mechanism I saw drawn was very close to perfect. Does this example make sense to everyone? Is everyone comfortable with the following example? Any questions on this example? Okay, let's keep going then. In this case, we have an intramolecular reaction. In terms of is anything else produced, we do see well, you're not really going to shift your, well, sure, you're also going to make H3O plus, but there's a ton of that sitting around. In terms of other alternative products, not as much in this case because our alkene is already the most stable alkene we can get. Like we are not going to see any hydride shifts or anything like that, or alternative elimination products. This system is very much set up for a reasonable amount of selectivity, though typically in these addition reactions, you can get some interesting products. Now, let's look at a reaction where instead of dealing with an intermolecular addition, our addition is occurring in an intramolecular perspective. So this we're dealing with just catalytic H+, so no water added. So there's no external nucleophile. And I'd like you to try and draw a mechanism for the following reaction. And we call this an intramolecular reaction. And you're welcome to draw the acid. You're welcome to draw the acid in this case as H3O plus. You're welcome to draw the acid as H3O plus, just to make it easier to draw the mechanism out. So let's take a moment. Let's try and draw the mechanism for the following intramolecular reaction. So there's no extra water added beyond the trace amount of acid needed to kickstart this reaction. And I'd like you to draw the mechanism for this reaction. It's very similar to the example we did earlier, except this time our nucleophile is in the same molecule. So don't be shy. Let's take about 2 to 3 minutes and let's try getting at least 1 to 2 responses using the annotate feature. Could you draw the first step where, so the internal nucleophile attacking looks good, but could you draw the first step where you protonate your alkene just to make sure the arrow pushing is perfect for that step? And you should draw your arrow pushing for the protonation step from your starting material. So you should start from your starting material and show the first protonation step. Yep, that looks good. Yeah, that's fine. You can draw it like that in this case. Whatever your acid is, you're breaking the acid H plus bond and you're protonating your alkene. Yep, that looks fine. And now you draw the cation after protonation and you just redraw the correct step that you drew at the start of this exercise. So you're very close to perfect. So once you drew this first step, you draw the product from that step, and then you keep going from there. Yep. Looks good. Yep. And now you draw the product from that step. So the mechanism is almost perfect. Let me clear. So you got all of the very key steps correct. But there's two details that you need to make sure you include. So first things first, in this case, you can draw your acid as H plus or whatever acid you're given. So if I said H3O plus, I draw H3O plus. We protonate our alkene. And just like before, we generate the most stable tertiary carbocation. Then we have an internal nucleophile. So our internal nucleophile will attack our carbocation and we generate the following cyclic intermediate. Now, the one thing that you need to make sure when you're drawing mechanisms is don't just randomly lose protons, because these protons are really important as they affect the reactivity of each of your atoms, and they help you see whether a reaction requires catalytic or stoichiometric acid. So your base can be anything from a reactant molecule to some water floating around, or depending on its basicity, the conjugate base of your acid. So our base is then going to deprotonate our water, or deprotonate our ether, sorry, and we'll generate our desired cyclic ether product. So this is an intramolecular reaction where both your nucleophile and electrophile are in the same molecule. The main feature of intramolecular reactions that I want you to know is that they're very fast. Why? Well, your nucleophile and electrophile are close together, so it's easier for them to bump and for a reaction to occur. Does this make sense to everyone? Mechanistically, the only thing that's changed is your nucleophile is an internal alcohol rather than external water. But on exams, you may see cases where you observe intramolecular reactions, and I just want you to know they're very fast. They will outcompete intermolecular reactions in most cases. Okay, let's look at a few more examples. So now we're going to talk about addition of halogens to alkenes. So bromine and chlorine add to alkenes to give 1,2-dihalides. Now, don't try this reaction with fluorine. Fluorine is too reactive. It's exothermic, and the reaction will run away from you very quickly. It's explosive when it reacts with alkenes. And for iodine, the product is typically unstable. So when you think of chlorine and bromine, I'd like you to think of it as like Cl plus and Cl minus, Br plus and Br minus. You have an electrophilic halogen atom and a nucleophilic halogen atom. So just in a broader perspective, halogens can add to alkenes to give a 1,2 dihalide. So in this case, ethylene gets converted to 1,2 dichloroethylene. Okay, in terms of the stereochemistry of halogen addition, the addition is exclusively trans. So the two halogen atoms are on opposite faces of our molecule. And we'll understand why that is by looking in detail to the mechanism behind this reaction. Okay, so you do not see the cis product. Do not draw the cis product for dihalogenation. It's important that we appreciate the stereoselectivity, because by appreciating the stereoselectivity, we can begin to utilize the stereoselectivity of these different reactions to produce our desired product. Okay. So we generate our trans addition product. Yes, they will both always be trans under these reaction conditions. Yes. Perfect. So let's talk about the mechanism of bromine addition. So we have electrophilic addition of bromine Br+ to give a cation, is then followed by cyclization to give what's known as a bromonium ion. Now, bromine can add to either face to generate a bromonium ion. And this was quite the vexing problem if you wanted to get enantioselective bromination to occur, because this bromonium ion can actually pass its bromine to another alkene, and you can potentially obliterate any enantioselectivity. There's work in recent years by the Burns group, among others, to develop methods for enantioselective dibromination and halohydrin formation. It's really quite interesting work. So with that aside out of the way, the bromonium ion is a reactive electrophile, and the bromide ion is a good nucleophile. Okay, so the bromide then attacks from the opposite face at the most substituted carbon. So I'd like to think of the most substituted carbon as the most carbocation-like carbon, yielding the trans addition product. Okay, so mechanistically, first things first, we have addition of Br+. Then we have the attack of Br- from the opposite face. And that in turn gives us the trans product. We'll draw a few more mechanisms for this reaction in a moment. So let's try to apply this idea to the following two examples. So our goal is to predict the products of the following reactions. And let's look at each of these examples individually. So first and foremost, let's look at example A. Okay, so we're going to start with example A and start with our substrate A. Okay. Here we go. So here's substrate A. We have bromine that I'm going to draw as Br. Oops, one moment. Let me get the zoom just right for this. Okay, there we go. So the first step mechanistically is that our alkene attacks in a concerted manner our bromine atom, and we generate our bromonium intermediate. So we don't generate a straight carbocation in this case. We're going through a bromonium intermediate. Now I'm just going to draw the attack from the top face, just so that way we don't have to draw so many arrows at once. Okay, so we have our bromine attacking from the top face. Let me make a model of this process, and I'd encourage you at home now to make a model of the following intermediate, and we'll talk about this reaction in detail in one moment. I'm just going to show you a model of our alkene and a model of our bromonium intermediate. So we're starting off with the cis alkene. So let me show you our starting material. Okay, so here is our cis alkene. Okay, does everyone notice how the methyl groups are cis? Okay, so our bromine equivalent is going to add from the top face. So from our perspective, it's going to add from the top face. It could just as easily add from the bottom face. So what I'm going to do is I'm going to make a model of our product after addition. Okay? I'm just showing that the bromine's attacking. I'm currently putting together the model of the bromonium intermediate that we generate. Okay, so just as a refresher once again. So here is our alkene. The bromine is going to attack from one of the faces. It's completely arbitrary what face it attacks from in this case. Okay? After the attack, notice how our methyl groups are cis still. In our bromonium intermediate, after the attack, does everyone notice how the bromine atom is now installed? Does everyone see how the bromine atom is now installed? Okay. Does everyone see how the methyl groups are still cis to each other? Does everyone see how the methyl groups are still cis? Okay, perfect. Now, if we tilt our perspective a little bit, okay. Yes, the bromonium ion does induce, the molecule itself is slightly polarized because this is a Br plus equivalent. Now in this case, both of our carbons are equally substituted. So we have free reign in terms of which carbon we can attack. But in terms of drawing out this first intermediate, my question to all of you is, are these methyl groups pointing towards us or away from us as drawn? Are they pointing towards us or away from us? Away. Okay, perfect. So I'm a big believer in the phrase, just draw what you see. Okay, so here's our bromonium intermediate. And now our bromine equivalent is going to come on in and it can attack from the back. And it can attack at either the left or the right carbon. In this case, they're equally substituted. So let's draw what would happen if it attacks at our left carbon, okay? So the bromine, Br minus, is going to attack at our left carbon, and we're going to break our carbon-bromine bond. Okay? So in turn, we get our trans addition product. And we'll worry about dash wedge in a moment. We'll worry about dash wedge in a moment. So allow me one moment to rearrange our model to show you the trans addition product if we add at the left carbon. Okay, so here we go. So as we notice, first and foremost, one of our bromines is pointing towards us. That's from our Bromonium Intermediate. The other bromine is pointing away from us. Now, what we also notice, whoops, sorry, I had it oriented the wrong way. Okay, here we go. Both of our methyls are still quote unquote cis relative to each other. And now what we're going to do is we're going to rotate our molecule so it's drawn in normal dash wedge notation. So we're going to rotate, in this case, we're going to rotate this left-hand side of our molecule. And then we're going to draw what we see in dash wedge notation. We're just going to draw what we see in dash wedge notation. Oops, let me get this set up so we can draw these in about as uniform of a way as possible. Okay, so initially we had both of our bromine atoms on opposite faces after the attack. Now what we're going to do is we're going to rotate our carbon-carbon bond and change our view of this molecule, and then we're just simply going to draw what we see. We're just going to draw what we see. So first things first, converting this structure into dash wedge notation. Converting this structure into dash wedge notation. Let's try to answer a few questions about this structure. So, we've rotated this bond, and now my question to all of you is, after we've drawn our basic 4-carbon skeleton, are the hydrogens, is this hydrogen here pointing towards us or away from us? Is this hydrogen pointing towards us or away from us? Towards, okay? Our bromine is then pointing away from us. Okay, let's keep going now. Is this hydrogen here pointing towards us or away from us? So is the second hydrogen pointing towards us or away from us? Towards us, okay? So let's draw the hydrogen with a dash, with a wedge, and then the bromine gets a dash. Okay, so just to give you a play-by-play one more time, of what happened here. Okay, so we started off with a bromonium intermediate. We started off with our bromonium intermediate. It was then attacked from the opposite face, and we in turn generated a dibromide product where the bromines are on opposite faces. Does everyone see how the bromines are on opposite faces? Does everyone see how the bromines are trans to each other? That's what we drew right here. Now we changed our viewpoint, and the way that we did that is we rotated our carbon-carbon bonds to give the typical straight chain zigzag pattern. Then what we did is we noted whether each of these two hydrogens were pointing towards us or away from us. We clearly see the hydrogens are pointing towards us, so they get wedges. The bromines get a dash. Does this make sense to everyone? So this is one of the products that we can observe. We also observe the opposite enantiomer. So suppose we had and generated a bromonium intermediate on the opposite face. So one thing I want you to appreciate is that when we look at this molecule in detail, this molecule is not perfectly symmetrical in this case. So we can have non-superimposable mirror images, depending on where our bromonium intermediate forms. So we also observe the enantiomer. Okay, so let's look at what happens when we change our olefin geometry. What happens if our alkene geometry is different? So let's look at the trans. Let's look at our trans olefin, or the E olefin, and see what happens. So just like before, bromine is going to react with our alkene in order to generate the bromonium intermediate. Now, what do we notice is slightly different about our bromonium intermediate? So let's take a moment and let's see if we can spot the major difference with our bromonium intermediate. Whoops. So we're just supposing that our bromine adds from the top face in this case. So let's show our alkene and let's try to draw our bromonium intermediate. So first and foremost, here is our alkene. Does everyone clearly see that we are dealing with a trans alkene? Okay, now bromine can add from either the top or the bottom face to make a bromonium intermediate. We're arbitrarily choosing the top face. The bottom face would give you the enantiomer that we keep talking about. Okay, So after give me one moment. It takes a little bit of coercing to get the model kit to want to make a bromonium intermediate. Okay, so here we go. Here's our bromonium intermediate. Does everyone notice how bromine has added from the face closest to us? Okay, does everyone see the trans relationship between our methyl groups right now? Does everyone see the trans relationship between our methyl groups? Okay, so now what we're going to do is we're going to attack our bromonium intermediate, and we can attack at either carbon. I'm going to arbitrarily choose the left carbon. If we attack on the right, we generate a slightly different product. Okay. So we are going to attack on our left-hand carbon. And now I'm going to show you, after addition, what the product looks like. So after addition, we have the trans addition product, but notice how the relative position of the methyl groups is different for our trans product. I'll now show you a model depicting our two products. One moment, putting together the model, and I would recommend you put together your own model at home as well. Okay, here we go. So here is our trans addition product. Notice how, does everyone agree that the bromines are on opposite faces? Does everyone agree that the bromines are on opposite faces? Okay, now my question to you is, does everyone notice how the methyl groups are also on different regions of space? They're also sort of on opposite faces as well. Does everyone see how the methyl groups are sort of on opposite faces as well? Okay, so now what we're going to do is we're going to rotate our molecule. We're going to rotate our molecule. And we're just going to configure it in the typical dash wedge notation. And now that all of our methyl groups are flat in the plane of the page, my question to all of you is, starting with this bromine on the left, is it pointing towards you or away from you? Is it pointing towards you or away from you? Towards. And is this hydrogen pointing towards you or away from you? Towards. Yep. Okay. So let's now draw what we see. So in turn, going from our initial rough sawhorse projection for our molecule looks something like this, and we translate it to the following dash wedge notation. So we've said first and foremost that one of our bromines is pointing towards us and the other bromine is pointing away from us. Let's check really quickly that our model matches what we've observed. Okay. Let me just correct this really quickly. Okay, so we started off with our trans addition product. We then rotated our molecule and we note whether the halogen is pointing towards or away from us. One of our bromines is pointing towards us. The other bromine is pointing away from us. Note, as we can potentially attack at another carbon, we would observe a mixture of enantiomers. So we also observe this alternative species. Now, one thing I want us to note is after rotation, if we take a look at the following molecule, is the following molecule symmetrical? After addition, is the dibromination product from our trans alkene, is it symmetrical? Yes. So these two species are meso. So as we notice, depending on the geometry of our olefin, whether it's Z or E, we get different dibromination products. Does that idea make sense to everyone? Does everyone see the relationship between our alkene geometry and the products generated? For our Z olefin, we generate one set of products. For our E olefin, we generate another set. So just to zoom out so everyone can take a picture of the two reaction pathways. Again, the trick for drawing the reaction products for dibromination is you draw out your bromonium intermediate, and then you draw the trans addition, you rotate your molecule, and then draw it in dash wedge notation. How do we know that it's rotated properly? As long as the carbons are all in the plane of the page, you're perfectly fine. Any other questions on this overview of dibromination? We'll have you now do a few examples predicting the products and drawing the products from this reaction. So let's have you work on the following example, the following reaction. So I'd like you to draw a mechanism for the following reaction, and I'd like you to predict the products of the following reaction. So this substrate is a little bit easier than the ones that we looked at earlier, but I just want to make sure that you're entertaining both bromonium intermediates. Remember, we can attack from the top or the bottom face. So let's take about 3 to 4 minutes to work on this example, and then we'll come together as a group to discuss. And don't be shy to break out the annotation tool and propose the products from this reaction. Oh, and don't be shy to start drawing out the mechanism. You're more than welcome to. And in fact, if we have two people draw the mechanism, we can entertain both the addition from the top face and the bottom face. So don't be shy here. And just remember to draw an arrow kicking the electrons back to the other bromine atom to generate bromide as well. And let's have green do the top face and pink can do the bottom face. Don't worry, mechanistically they behave the same, but I just want you to draw those products so that way we can compare them. Yep, good, good. Top face pointing towards us, looks good so far. And just don't forget the other arrow kicking the electrons back to the bromine to make bromide. But otherwise, the mechanism looks good so far. Yep, yep. That looks good so far. Now just draw the trans addition product. Yep, for green, you're on the right track. All I need is for you to draw the product from this attack. Sure, sure. If you're making a model of it, you're more than welcome to share it. Yep, that looks perfect. That looks perfect. Yep, exactly right. Mm-hmm, perfect. So I notice I notice everyone's getting a little bit stuck assigning the stereochemistry. That's okay. Let's talk about this and let's use our model to help us out. So we're going to now entertain multiple possibilities for the addition. So the first step, let's look at addition from the top face. So we have our alkene, and our bromine is going to add from the top face, arbitrarily, of course. Okay, so our alkene attacks, bromine attacks, and we generate the following product. Okay, so we have our bromonium intermediate. Let me redraw this so we have a little more space to work with. Okay, so to show you what this bromonium intermediate looks like, here we go. So here's our bromonium intermediate. Let me put the methyls in just for good measure. Okay, so here is our bromonium intermediate with both of our methyls. Okay? Now, we can attack this bromonium intermediate from either the right-hand side or the left-hand side. Doesn't matter which. Let's arbitrarily choose the left-hand side. So let's draw our attack. The attack is going to occur from the bottom face. To give our trans product. So we have one of our bromines pointing up and the other bromine pointing down. This product looks like this. One of our bromines is up, the other bromine is down. So then, when one of our bromines is up, is one of our other methyls also up? Yes or no? Is one of our methyls also up? Yes. Okay. So we can draw one of our products. As so. So we have the bromine up and the other bromine down and both of our methyls, which you can draw this as bromine up, methyl up, methyl, methyl, whatever you prefer. Let's now entertain the enantiomer. So let's look at the attack from the bottom face. So we're going to draw our exact same alkene, except this time our bromine will attack from the bottom face. Okay, that generates the following bromonium intermediate. For those curious as to why I didn't draw the regioisomer, that's mildly redundant, as the regioisomer, this molecule is symmetrical. One moment, just getting my model kit to close the bromonium properly. Okay, so here's our bromonium formed from the attack on the bottom face. Does everyone notice how the bromine is now on the bottom face? It's on the bottom face of our plane. Notice this bromonium intermediate is symmetrical, it's meso. We won't worry too much about that for now, but just something to note. Now we can attack with bromine from the top face at either carbon. Whoops, sorry about that. At either carbon, so right or the left. Let's arbitrarily attack at the left carbon. Just completely arbitrary. Both carbons have equal reactivity. Okay, so we attacked, and we now have the following trans bromine addition product. Okay, so now all we have to do is draw what we see. Let me adjust this really quickly so we have sorry about that, just adjusting the model since our camera has mirrored my structure. Here we go. So we have the following trans bromine addition product. After bromine attacks, arbitrarily, we're going to have bromide attack at the right-hand carbon, and we generate the following structure. So one of our bromines is pointing up, the other bromine is pointing down, and we have our methyls. So looking at these two products are enantiomers. So non-superimposable mirror images. So the enantiomeric products stem from the fact that we can generate our bromonium on two different faces, which in turn, after attack on our bromonium intermediate, generates two different products. Does this make sense to everyone now? Does everyone get why we get a mixture of enantiomers? Because we have two faces to choose from for our bromonium addition. Perfect. So always make sure to indicate your enantiomers and then check to see if your enantiomers are meso or not. So looking at this molecule, after rotation, these two molecules are not superimposable. Okay. Let's talk about a case where we can observe diastereomeric products. So following up on our idea of addition of halogens to alkenes, these bromonium and halonium intermediates can be intercepted with other nucleophiles, such as water, alcohol, or internal nucleophiles. And we can use this to make very interesting species. The first example of this would be making halohydrins from alkenes. So the active reagent is our dihalogen in water as a co-solvent. So we take our alkene, and if we add our halogen in the presence of water, we end up with addition of water and our halogen. We call this a halohydrin. Now, to accomplish halohydrin formation, N-bromosuccinimide, otherwise known as NBS, is used as a common source of Br+ to minimize the competing addition of bromine to our alkene. So N-bromosuccinimide is thought of as the source of Br+. So it's commonly used for halohydrin formation because we don't have an equivalent of Br- floating around. Okay, so let's talk about the mechanism for halohydrin formation. So first and foremost, Br plus adds to either face of the alkene, and that in turn generates a bromonium intermediate. Okay? Water then attacks, just like always, from the opposite face of the bromonium ion, yielding the trans product, otherwise known as the anti-addition product. Just like before, water will attack the most substituted carbon, or the carbon that has the most cationic character. Okay, and in this case, the regioselectivity is important. So again, the reason why we observe the trans product is water is attacking from the least hindered face opposite to our bromonium. Okay. Let's look at some examples and let's try to rationalize selectivity. So halohydrin formation, just like alkene addition, although halohydrin formation doesn't proceed through a formal carbocation, it still follows Markovnikov selectivity, where addition of alcohol or water occurs at the most substituted carbon that can most readily stabilize a positive charge. So if we think about these two sites, a primary versus a secondary, which of these two sites, the primary or the secondary benzylic site, is more readily able to stabilize a carbocation? Which site is more likely to have a partial positive character? The benzylic site, yep. So we can say that this site can readily stabilize a positive charge. Okay, and so that is why we see addition at our benzylic site. So to help explain this idea, although a formal cation isn't generated, the carbon-bromine bond attached to the more substituted carbon, or the carbon that can more readily stabilize a positive charge, is weaker and more reactive towards displacement. So notice how this bond, this carbon-bromine bond, is weaker. And as a result, addition of water occurs at the carbon that can most readily stabilize a building positive charge. Does this make sense to everyone? Why, if we compare a secondary and tertiary site, water prefers to add at the tertiary site? Does this make sense from our discussion of Markovnikov's rule? Okay. So one thing to note, we are not making a formal carbocation. We are not making a formal carbocation. It's just the fact that this intermediate, the carbon-bromine bond, is weaker when it's attached to a carbon that can readily stabilize a positive charge. We don't see any weird carbocation shifts in these reactions, and that's what makes them particularly useful. We get Markovnikov selectivity without having to go through carbocation intermediate. Well, concerted refers to both steps occurring at once, but this is clearly bromine adds, then water attacks from the opposite face. But you can consider it as the addition of water and the breaking of the carbon-bromine bond occurs simultaneously. So that step is concerted, if that can answer your question. Okay, perfect. So the fact that we're not going through a carbocationic intermediate allows us to get this stereoselectivity. Pretty cool. Okay. So we can also react our halonium intermediates with alcohols or internal nucleophiles. So if we use an alcohol, we would also observe a chlorohydrin generated. Now, one thing that's really cool, and this is commonly applied even in modern total synthesis, is that if an internal nucleophile reacts with a halonium intermediate, the stereochemistry of the nucleophile can influence the stereochemistry of the products. Okay, so does everyone notice how our nucleophile is bonded to our cyclohexane ring with a wedge? How it's pointing up out of the page. Does everyone notice that? Okay, so this nucleophile, this internal nucleophile, is stuck on the top face. It can't bend around to the bottom face. It's stuck approaching from the top face. So then, when you generate your halonium intermediate, the attack occurs selectively from the top face. And this is just a beautiful example of utilizing your substrate to skew the selectivity of your reaction. So we've tethered our nucleophile. So the cyclization occurs in an intramolecular fashion, and it occurs selectively with an attack from the top face. Pretty cool, right? Okay, so what we're going to do is we're going to tackle these next two examples. So I always like to include an E and a Z olefin for analysis. In this case, we have an E olefin to analyze. And let's try to predict the products of the reaction by drawing each step mechanistically. So even though you're not formally asked to draw a mechanism, it's important to go through with a mechanistic understanding to begin to predict the products. So the first step, we have N-bromosuccinimide. So I'm going to draw N-bromosuccinimide. Our alkene is going to attack our N-bromosuccinimide, and we're going to generate our bromonium intermediate. We're going to respect the fact that these methyl groups are cis, and we're going to draw addition of our bromine from the top face. So we have our bromonium intermediate. Allow me a moment to make a model of this intermediate. I'm just checking that. Okay, halfway there. First, let's show the alkene, then let's show the bromonium intermediate, and finally, once we have our bromonium intermediate established, then we will show everyone the addition product. Okay, so here is our alkene. Recall that bromine can add from the top or the bottom face. We're going to add arbitrarily from the top face closest to us. Let's now make a model of our bromonium intermediate. Let's now make a model of our bromonium intermediate. And I'd really like you to follow along at home and when you put together your model, as it's really invaluable towards starting to visualize how these reactions behave. And just be careful not to accidentally break your model kit when you're making these bromonium intermediates. Okay, so here we go. Here is our, whoops, let me rotate that around. Okay, so here is our bromonium intermediate. We're now going to attack it from the opposite face, and we're going to arbitrarily choose one of our carbons to attack. In this case, is there some bias here? When we have our nucleophile, in this case, our nucleophile of water, which site is preferred, site A or site B? Which site gets attacked? Which site is more substituted? B, exactly right. So we're going to attack from the opposite face at carbon B. So we have our water. So we have water, and water is going to attack at our most substituted carbon, which is on, from your view, the right-hand side. So let's now draw the product after attack. Okay, here we go. So as we can clearly see, our bromine and water are on opposite faces. Perfect. Let's just take a look at a moment at our methyl groups. Are both of our methyl groups still in the same face? Are both of our methyl groups still on the same face? Are they still on the same side of our molecule? Yes. Okay, so what we're going to do now is we're going to rotate our carbon-carbon bonds to get our structure in zigzag form. And now all we're going to do is we're going to answer the question, is the group closer to me or farther away to me? So first and foremost, is this hydrogen attached to our carbon, attached to the bromine? Is this hydrogen pointing towards you or away from you? Towards you or away from you? Towards. So the hydrogen gets a wedge. Let me rotate this molecule just a little bit. There are many ways for drawing this molecule and for drawing the range of products that you'd observe from this reaction. I'm just trying to check to make sure. I'm just checking to make sure that that we're preserving stereochemistry. So the product that we're showing in the models is a mirror image of the product that we're dealing with here. So the bromine is pointing out of the plane of the page. And now looking at the following structure and drawing what we see. Is this alcohol pointing out of the plane of the page or into the plane of the page? Is the alcohol pointing out of the plane of the page or into the plane of the page? It's pointing towards us, yep. Okay, so we give our alcohol a wedge. Okay. And our ethyl group gets a dash. In our last step, we remove and we deprotonate our alcohol with water to give the following product after addition. So let's go through the steps one more time for this process. Let's go through the steps just one more time for this process to help us visualize and understand what's going on in this example. So first and foremost, we generate our Bromonium Intermediate. Here we go. So as we can clearly see, both of our methyl groups are cis to each other. Then we attack our Bromonium Intermediate. We attack our Bromonium Intermediate from the most substituted carbon. So we're attacking, in this case, from the carbon with the ethyl and the methyl group. We open up our Bromonium Intermediate. So we open up our Bromonium Intermediate. And we observe the trans addition product. Now, what we did is we rotated our molecule so all of our carbons were in the plane of the page. Okay? And now what we're going to do, let's rotate it the other way to make it a little easier to see. And now all that we did, now that we've rotated each of our carbons so they're in the plane of the page, does everyone see the characteristic zigzag? Does everyone see the 4-carbon zigzag that we generated? Okay. And now all we did was we designated whether our species is pointing out of the page or into the page. And we noted both our alcohol and our bromine were pointing out of the page. And that in turn gives us the following product. We also observe the enantiomer, which the enantiomer looks something like this, with both the bromine and the alcohol pointing into the plane of the page. So we went a little bit over, so we're going to take a 10-minute break, and then we'll resume in